Welcome to Cambridge IGCSE Physics, Lesson 47.1, Turning Effect on Current Carrying Coil. This is core content for the Cambridge International General Certificate of Secondary Education Physics, Syllabus 0625. Today we explore how current carrying coils experience forces in magnetic fields leading to rotational motion. This principle forms the foundation of electric motors and many electromagnetic devices used worldwide. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know that a current-carrying coil in a magnetic field experiences a turning effect. Understand the factors that increase this turning effect. Know specifically that more turns in the coil, more current through the coil, and a stronger magnetic field all increase the turning effect. These objectives align with Cambridge IGCSE assessment objectives, A01 for scientific knowledge, A02 for problem-solving application, and A03 for experimental analysis skills. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, turning effect, which means the rotational force experienced by a current-carrying conductor in a magnetic field. Second, coil, which means multiple loops of conducting wire wound together to form a circuit component. Third, torque, pronounced torque, which means the measure of how much rotational force is applied to an object. The motor principle states that a current-carrying conductor in a magnetic field experiences a force. Understanding these terms precisely is crucial for mastering electromagnetic concepts. Let's explore our first core concept. The fundamental principle states that a current-carrying coil placed in a magnetic field experiences a turning effect. This means the coil will rotate about its axis. The definition is, each side of the coil carries current in opposite directions, so experiences forces in opposite directions, creating rotational motion. Mathematically, we express the force on each side as F equals BIL, where F represents force measured in newtons, B represents magnetic field strength measured in Tesla, I represents current measured in amperes, and L represents the length of conductor measured in meters. The diagram illustrates a rectangular coil in a uniform magnetic field. Notice how the left side has current going into the page while the right side has current coming out. This creates opposing forces that cause rotation. Now we examine the factors affecting the turning effect. This follows Cambridge IGCSE core requirements. Three key factors determine the magnitude of the turning effect. First, the number of turns in the coil. More turns mean more current-carrying conductors in the field, so greater total force and turning effect. Second, the current magnitude. Higher current through each conductor increases the force on each turn, increasing the overall turning effect. Third, the magnetic field strength. A stronger field exerts greater force on each current-carrying conductor. The combined effect shows that torque, the turning effect, is proportional to N times 1 times B, where N is number of turns, I is current, and B is magnetic field strength. Let's work through our first example. The problem states, a rectangular coil has 50 turns, carries 2.0 amperes current in a 0.15 Tesla magnetic field. Each turn measures 0.08 meters by 0.06 meters. Calculate the force on one long side. We are given N equals 50 turns, I equals 2.0 amperes, B equals 0.15 Tesla, and L equals 0.08 meters for the long side. We need to find the force on one long side. Step 1. Write the equation. We use F equals BIL, where F is force, B is magnetic field strength, I is current, and L is length. Step 2. Substitute the values. We write F equals 0.15 Tesla times 2.0 amperes times 0.08 meters. Step 3. Calculate. F equals 0.024 newtons. Step 4. State the answer. The force is 0.024 newtons to two significant figures. Example 2 applies the same principle to compare different coils. The problem is, compare the turning effects of coil A with 20 turns carrying 1.5 amperes versus coil B with 30 turns carrying 1.0 amperes. The data shows both coils have the same field strength and dimensions. Now we analyze. First, calculate N times I for coil A. This gives 20 times 1.5 equals 30. Second, calculate N times I for coil B. This gives 30 times 1.0 equals 30. Third, compare the ratios. Both products equal 30, so the ratio is 1 to 1. Fourth, state the conclusion. Both coils experience identical turning effects because the product of turns and current is the same. The graph shows both coils have equal n times 1 values, confirming equal turning effects. Mathematical skills are crucial in electromagnetic physics. Let's examine 3 key skills. First, proportional relationships. When torque is proportional to N times Y times B, this means doubling any single factor doubles the torque. If the number of turns increases by a factor of 3, the torque increases by a factor of 3, assuming current and field remain constant. Second, force calculation on coil sides. Each side experiences force F equals BIL, but the forces act in opposite directions on opposite sides, creating rotational motion rather than linear motion. Third, comparing motor performance. To compare different motor designs, calculate the N times Y times B product for each. The motor with the larger product will have greater turning effect and better performance. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, state 3 factors that increase the turning effect on a current carrying coil. This tests your knowledge of the fundamental concepts. Question 2 is intermediate level. It states, a coil has 40 turns, carries 1.8 amperes current in a 0.12 Tesla magnetic field. Calculate the force on a 0.05 meter side. This requires you to apply the force equation we learned. Question 3 is advanced level. The question is, explain why a coil rotates continuously in an electric motor design. This tests your analytical understanding of practical applications. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how today's concepts apply in practice. In electric motors, the turning effect on current-carrying coils drives everything from electric cars to household appliances and industrial machinery. The same principle enables precise control of motor speed and torque. In renewable energy, wind turbines use the reverse principle. Mechanical rotation generates electrical current through electromagnetic induction. In medical technology, MRI machines use complex electromagnetic coil systems to create strong, precisely controlled magnetic fields for body imaging. These applications show why understanding electromagnetic forces matters. Career-wise, this knowledge leads to electrical engineering designing efficient motors, renewable energy engineering developing wind and hydroelectric systems, and medical physics creating advanced diagnostic equipment. Let's review the solutions. For question 1, the answer is more turns in the coil, greater current through the coil, and stronger magnetic field. These are the 3 factors that increase turning effect. For question 2, we use F equals BIL. Substituting F equals 0.12 Tesla times 1.8 amperes times 0.05 meters, which equals 0.0108 newtons. For question 3, the coil rotates continuously because the commutator reverses the current direction every half turn, maintaining consistent rotation direction. Without this reversal, the coil would oscillate rather than rotate. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every calculation step. Third, check if your answer is reasonable. Forces should be small values in typical school experiments. Fourth, read questions carefully. State means list facts. Calculate means find numerical answers. Explain means give reasons. Let's summarize today's lesson. The key points to remember are, first, the motor effect. A current-carrying coil placed in a magnetic field experiences a turning effect due to forces acting on opposite sides in opposite directions. This is fundamental to understanding electromagnetic rotation. Second, 3 factors control the magnitude of this effect. More turns in the coil, greater current through the coil, and stronger magnetic field all increase the turning effect proportionally. Third, applications include electric motors in vehicles and appliances, generators in power stations, and medical equipment like MRI scanners. For further study, review the force equation F equals BIL and understand how it applies to each side of a coil. Practice calculations involving motor effects and turning forces. The next lesson covers electromagnetic induction, which is the reverse process. how moving conductors in magnetic fields generate electrical current. Today's motor effect knowledge provides the foundation for understanding generators and transformers.